Hello and welcome everyone to the 2017 security presentation. I'm going to be going through a post-attack analysis of the XOR DDoS that happened, and a little bit of background on that. In September of 2015, there was quite a large DDoS attack, over 150 gigabits per second, and it made just the regular news. What was a little bit interesting about this one is that it was Linux malware. You'll see where we got the name XOR DDoS from in a couple of slides here. It targeted Linux devices, of course, as well as IoT in x86, AMD, and surprisingly ARM, but though we didn't really see that much in public. This was a brute force attack using secure shell. We'll talk about that a little bit. It used a rootkit to cover its tracks and had the standard command and control, controlling all of the attack activities. And this was a little bit ago in terms of time, but we're still seeing XOR DDoS derivatives today. So what often happens is somebody will have an attack based on some malware, and then that malware gets modified and people come out with new variants of this by different attackers. So right at the beginning, let's just jump into what is a brute force attack and how did they get in on that? Well, basically that means to guess as many passwords as possible until you get the correct one. This can be quite easy if the password is short, but quite difficult, if not impossible, once you get to longer and more complex passwords. To speed up the processing, what attackers usually do is use dictionaries of common words, previously seen passwords, and a little bit of modifications on those. Another thing that's somewhat related to this are rainbow tables. Those are pre-calculated values of a complete set of, for example, like a password length that they've pre-calculated ahead of time. But these really weren't used in the XOR DDoS attack. They were more, because this was an attack over the internet and not a local attack, it was more about smart password dictionaries that were used. So here's an interesting graphic that a person on Reddit came up with and did some analysis on what a brute force looks like. And they basically did a calculation between the length of the password and the number of different values that could be in there, and they attribute that to entropy. And so if you can use, if you require 8 characters, and whether or not it's upper and lowercase, special characters, you know, all those things that we hate having when we create passwords. Depending on all of that, this person has done a great presentation that shows you how quickly you can, in general, break into one of those passwords. Again, assuming pure randomness here in terms of the attack, and not necessarily getting lucky with smart passwords. You can buy smart attack passwords for $30 if you want something that's pre-done, that's got, you know, some analysis on it. There's of course a whole bunch of free stuff that you can do yourself, but heck, for 30 bucks, it gives you a great starting spot. And it's not just the common words. So I know a lot of us tend to, on a password, just append one number or 2 numbers or something like that. It's super easy to use these word lists, and you can simply say, use a common word and add a number digit at the end of it. And the attack system will go through and try to do that. So adding a number to the end really doesn't save you much. It doesn't add much protection anyway. So here is an example of what the attack process looked like for XOR DDoS. And I found a picture. One of the best pictures I found was from the FireEye blog. And I thought, instead of just trying to recreate this myself, I'm going to use their fantastic picture throughout my description of the attack. So what they noticed in the first attack was that there were about 20,000 SSH login attempts in the first, 24 to 36 hours. So there was a big attack. Presumably this was the most common passwords for the country that they were trying to attack into. If you're attacking in the United States, you'd use English-based dictionary here. The phase 2, after that initial attack, if it didn't get anything, what appears they would switch dictionaries and just try another dictionary or 2, but it seemed somewhat half-hearted. And then it went into a long-term mode where the attack was just occasionally trying to break into the system, but the easy part they weren't able to get. So they're now in this long-term mode where if they get lucky, great, but they're just going to move on and try to find something that's easy. So that kind of shows you one of the benefits of a nice strong password. What's kind of scary here is the initial path that they're trying to take is the root account via SSH. So obviously these machines were configured to allow that to happen, and you'll see at the end, um, certainly not a good recommendation to have root directly accessible on the internet. And then upon success, if it does actually get a password, it really just logs out immediately, stops the attack because it's got extra phases it wants to do. And so this is just phase one that I've highlighted in red there. Just try to break in. If you break in, that starts you on the next attack. And the next phase, two, you can see here over on the right-hand side, the attack server will now connect in and runs a remote command. What's somewhat interesting about that is some versions of Linux do not log these remote commands themselves. So you might get a log and a debug log or something like that, but it doesn't log what actual commands on there. And that's kind of important because if you see some of these commands, you might want to do some automated log processing and do something with it. So that is interesting. But note, it is trying to SSH into the box because it does have the username and password. Now it's going to try to do something bad to it. And what that is, it's downloading a file, 3502.rar, and in that, it's looking at a bunch of IP addresses to attempt to grab this file down. Now, this file itself, and this where it comes from a little bit of obfuscation here, but it's just another shell script once you uncompress it, the 3502 RAR file. This is where it gets its name of XOR DDoS, and it uses a simple substitution to get into it. And I did just a basic little Perl script, uses a function called transliterate, and it just takes one character on the left, one character on the right, and swaps them in and out. So kind of a substitution, simple substitution kind of cipher. And when you do that and you take a look at the 3502 script itself, you can see that they've encrypted all of the IP addresses. Of course, if you're creating some kind of trigger on this, a Yara rule or something like that, you could do it on these bad IP addresses, but you could also do it on the encrypted information. So it just depends on how you're trying to scan for this information and whether or not you track it. But now that it's run that file and it's running local on the machine, the next step it's trying to do is it's trying to determine the kernel version of that compromised Linux server, and that's called the vermagic string. And what it does is it uses lsmod to get all of the modules, and then I think it picks the last one, last module, and then uses modinfo. And then you can see I've circled the vermagic string, and that tells you exactly the version number because it's pretty ingenious what it's trying to do. Its ultimate goal is to build this rootkit if it can, but it's looking to see what it's got. So at this point, the machine will say, hey, I've got this vermagic string, goes to a build server and says, do you have a kernel? Have you seen this kernel before? Because I want to have a rootkit specifically designed for this kernel, and it has to match. If that vermagic string doesn't match, Linux is not going to run this executable, if you will, and therefore it will fail. So each new machine that gets broken into, there's a vermagic string. That version string is sent to the build server, and if the build server has seen it, then it can return something appropriate. If, on the other hand, the build server has not seen that vermagic kernel before, what it does is it tries to gather all of the header files on the compromised machine, and it's going to ask the build server to build a custom rootkit just for that. So if those files are available, those header files are available, compacts them all up together, sends them to the build server, and asks the build server to compile a new version. And of course, it keeps that around. So if that ver magic string ever comes back in again, this build server already has it and it immediately downloads it, even if that machine didn't have all of the header files or anything like that. So it's a pretty smart system that they've built here. If, on the other hand, the build server, let's say it didn't have it, and the compromised server didn't have the headers, then the Trojan that gets returned doesn't have the rootkit. So it's this trade-off. The best option from the attacker's point of view is that the Trojan comes back with a rootkit so that it can hide itself. But if it can't do that, it'll still just return a Trojan. It's just easier to identify and easier to remove without it. So that's why they go through all this extra trouble just so that it stays on the server longer and it is undetected longer. All right, finally, there's a lot of steps here, but we're finally getting to the point where the machine uses wget to get the specific malware itself. And the malware is in ELF, which is basically like a Windows exe. An ELF is just an executable and linkable format, and it just stores it, on the compromised server. The rootkit itself, if it has it, is an LKM, a loadable kernel module. And now the Trojan is loaded with or without that rootkit. And then it will connect back into its command and control center. And that's the thing that's giving it its list of commands to do. And this is really my favorite part, if you can have a favorite part of malware, but it's my favorite part of what these developers did, is the first thing that the malware does when it's running on the compromised server, it says, hey, are there any other bad guys here? And if so, I'm going to kill their malware. Basically, they want the machine to themselves. So they're going to get rid of any other malware that they find on the machine and take it over completely from itself. That way, all resources can be used for, bad things, which you'll see. The bad things are going to be listening for attacks on DDoS. These are kind of volumetric flooding type attacks. So it can start or stop attacks based on destinations, IP addresses it wants to attack. You can download and execute new files. It'll update itself if there's new versions, get processes and memory listing if it needs to get more information or wants to kill other processes or something like that. It's pretty advanced system. And finally, I think the step 7 is the malware is going to do these DDoS attacks in 3 different ways: SYN, UDP, or TCP. And again, these are floods, volumetric, large-scale attacks. I think I mentioned at the beginning 150 gigabits was what we were seeing at the initial time of launch in 2015. And now the Trojan's just really working on its own. Downloads, execute commands. If a system administrator finds the malware and tries to remove part of it, it's going to reinstall itself. And then it just keeps on performing new commands. And it's just an automated system, and the attacker hopes nobody notices it. Well, the persistent mechanism is also pretty difficult of what they've done. There's a couple of variations of what the developers did to attempt to hide itself and to attempt to make it a little more difficult for cleaning. I'm not going to read all of the bullets here, but it copies itself, as you can see from the screen here. It copies itself into a bunch of different places. It creates symlinks in a bunch of different locations. It creates a cron script to make sure that it stays in there, and this persistent mechanism had a certain XOR key that I've listed here. But later variants that came out, and if anything new is coming out, you can imagine that it would look possibly similar, or they've done a whole new approach. So that's a little frustrating thing. It changes over time. So when that got live into the public, there was quite a bit of attacking going on in a whole bunch of environments. And on our CDN, we of course noticed the attacks immediately. And here's what we found in 2015 and 2016. This is part of CDNetworks XOR DDoS analysis report, and we've got it on our website if somebody wants to dive into more details here. But you can see on the table I've got here of the different attacks over the 2 years. A lot of it was pretty similar, but some things did change over time. The attack size themselves were 50 to 60 gigabits, and I don't know, 8 to 12 billion packets per second. In the scheme of things, this is not really a large attack at all. Now, it could be difficult for an individual business to handle, depending on what your network size is, what your ISP link is, and what kind of firewall and DDoS devices you have. If you've got 55 gigabits per second, or you've got 150 gigabits, those can be big attacks. And today we're seeing attacks that are 10 times larger than this, and greater than that. So 55 was not too hard to handle. You can see that there's different variations. The length of the attack, again, was not too long, but other types of attacks that happen in the DDoS world last longer than 6 to 8 hours. So in some sense, it's not too long. But of course, if it's Friday on a big sale that you're running on your e-commerce site, 6 hours would be far too long. Here's just a couple of months. You can see some particular details of how it was. Basically, what it looks like is the attackers were probably getting paid by people to run attacks, and it just was only a couple of hours, and some or most of the machines that they had compromised. So they'll basically presumably paying bitcoins, and you can run an attack kind of as anonymous as possible out there. We found, at least in the attacks that came into CDNetworks, the origins was primarily in two locations. Focus between here and China. A lot of other countries just had a very small amount of attack traffic. On the countermeasure side, there are a number of things that you could do, and somebody could do a full-blown presentation. Just a network security person could do a full-blown presentation on different countermeasures. But here's a couple that I found interesting, and you could run at times yourself. Of course, a CDN is going to do these depending on what the attack looks like. You've got to respond, and then the attacker does something, and you have to respond again. But one of the first things that was noticed was that the SYN packets had data in them. Now, normally that's not required by the spec, but if you put data in there, it just requires the routers and other devices to spend a little bit more time processing all of these things. So, potentially you could put in a rule for a certain amount of time to look for SYN packets with data values and drop those. You wouldn't want to make it a permanent rule, and you would want to check over what you're blocking, but that's certainly an identifier that you could use to block traffic. Another countermeasure that you can use is SYN cookies. This also blocks SYN spoofing type attacks. I think we all know a normal TCP connection's got this three-phase part. It's got a SYN, ACK, and then you finally get the ACK to get going. Well, a SYN cookie, somewhat like a web browser cookie, but purely on the network side. The client, in this case, if it's a bad guy, they often don't follow all of the rules of TCP because they've just got a cut down client that is just used for attack modes. So the first client sends in the SYN, like you see over on the left-hand side. And what we do, or maybe you could configure your firewall to do, is we set a special cookie value in the sequence. And that cookie value is manipulated when the client sends the ACK back. If they don't send the ACK back and do a +1 or this arithmetic calculation to it, then we know that It didn't have a full-blown client, and this often stops a lot of the bots that are out there, these types of attacks. If you're just trying a flood attack, this often stops a lot of them. So you can easily put this one in, and then we would block the attack if the cookie didn't come back the way that we were expecting it. Otherwise, regular traffic comes in as you'd expect. Another one that's somewhat similar to this is just a SYN drop, a temporary solution you might put in place to overcome an attack. It's also known as a SYN retransmission. And you can see over on the right-hand side, at first you send a SYN for the client sends it in, and then we in the cloud or maybe your firewall device would just drop the first one. We just ignore it. Now again, a well-formed client that's using full TCP is going to retry another SYN really quickly. But a lot of these malware devices don't do that. And so if they don't follow the rules, we just block them on the edge. And if they do follow the rules, good traffic comes in and it goes through the next set of security standards. So on the edge, one has to have multiple layers of security checking to be able to block all of this kind of traffic. Here's some countermeasures on the SSH side that sysadmins can use to lock down their servers a little bit, a little bit more, especially all the folks that got unfortunately successfully attacked. One, you can set up ACLs, access control list, to only allow certain IP addresses to access the server that you want SSH into. Certainly don't allow root login from the external internet. SSH keys, I think we all know, are better than passwords. Longer, more difficult passwords are better than simple ones. Two-factor authentication seems like a must-have nowadays. What really tripped up a bunch of these guys, though, was just not even setting port limits. So there's a couple of settings that they could have set, like max sessions and max authentication tries, and this would have stopped the random guessing. If you could only guess 3 times before you got somewhat locked out, that would have stopped a lot of successful intrusions. It's kind of like your bank, right? You can only try so many times. But unfortunately, a lot of these servers that were out there, and even more scary, a lot of default implementations of IoT devices come in without any of these settings in place. And you can just keep attacking these things for hours and hours and hours, and it's an automated process. And eventually you get lucky and you get in, and you get hundreds or thousands of these servers. Crazy. Going up to scale, SE Linux is available, though I often hear can be quite a bit more difficult to configure, especially with a bunch of applications. Scanning of log files like fail to ban and intrusion detection and prevention like snort and things like that are great things you can do. And sure, you can always change the default port number. That might reduce a couple of log entries, but it's not going to do much more than that. And here is how to remove it. This was at least one variant. Again, the different variants out there had different ways of removing it. What tripped everyone out in the beginning is they found the process that was causing the problem, and they would just go in and kill that process. Well, because of all of the actions behind the scenes, like the cron file, it would just reinstall itself all of the time. So you think you've killed it, but it just comes back at some point later. So that gets to be really frustrating. And the trick to this turned out to be that you need to pause it or stop the process. So you find that main parent process that is being executed, and you stop it with the kill command, kill-stop. That will start a chain for all of the children that are part of the process as well. All the children will die quickly because they can't speak to the parent anymore. Then you can go out and delete the files in all the different locations like user bin, etc, init.d, boot bin. There's a bunch of stuff, locations that it was in there, and you could see that original slide I had as well. You got to clean out the cron file itself. Get rid of the entries inside of there in the lib directory, all that kind of stuff. Once you've kind of cleared it out, cleared the cron type things, then you kill that parent process, and then the whole thing goes away. And that was the trick that everyone had to figure out. Of course, if you're running virtual servers and you just kill this one and spin up a new one, hey, that would be the easiest thing. But not all devices can do that, and IoT devices can't do that. So this was one variant on how to clear it. So kind of in summary here, really everything is vulnerable, and you just have to take the mindset that it's vulnerable and do a lot more testing, especially from the outside looking in. And you can see all of those devices that were broken into had some pretty basic configuration errors that didn't happen. So everything needs to be hardened. You need to test everything to ensure your security is in place. Make sure you've got a large enough network connection and scrubbing equipment to attack these, to be able to stop these DDoS attacks. 150 gigabits in 2015 was not that large. We're seeing 500 gigabit, 700 gigabit, 1,000 gigabit attacks that are happening. So the attacks are only getting larger, and it is more difficult to do this with your own on-premise hardware. So CDN industry and other cloud providers can generally have that much larger scale that can take that brunt on the edge for you before that traffic gets back to your origin. And on the acknowledgement side, there was a bunch of great information on this. Vast Blogs was fantastic, and you saw that I took a bunch of graphics from FireEye's blog as well. CDNetworks, we wrote a white paper that's available on our website. And if you want the most detailed analysis of the malware down to the assembly language level, Malware Must Die is a fantastic site, but it dives very deep. And again, and that's it for me. Want to thank everybody for attending the webinar, and we'll see you on the next time.